We have two more presentations today, this afternoon. The next is going to be by Marika, Holland. Marika is a climate scientist with the National Center for Atmospheric Research, and she is the chair of the Search Scientific Steering Committee. Marika?
So good afternoon, everyone. So as Brendan said, I'm Marika Holland. I'm a scientist at the National Center for Atmospheric Research. And today I'm going to be talking about how models and predictions from these models have the potential to inform the future. So I think it's useful for us to start out by thinking about what the Arctic might look like in 2050. So just imagine the Arctic in 2050. What changes might occur in the next 30 years? What thresholds might we pass in the Arctic? How might changes in the Arctic reverberate throughout the globe? This is a really challenging question to get our head around. And that's in part because this image of a melting Arctic is not from the future. This is from this year. And so we know that the Arctic is changing, and the Arctic as we know it is disappearing. We've seen rapid sea ice loss. We've seen increased melting of the Greenland ice sheet. That water is entering the ocean and causing sea level to rise globally. We've seen a warming in the Arctic, which is twice the rate of the global average. And we've seen extreme warm events occurring in the Arctic over the ocean and the land. We're seeing changes occurring across the Arctic landscape. Increased wildfires, increased coastal erosion, permafrost thawing, increased wave activity on the coastlines. We could go on and on. The entire Arctic system is undergoing this dramatic, rapid, unprecedented change. And what that means is that our traditional knowledge on how the Arctic works, what we can expect for safety of sea ice during different times of the year, that knowledge is being challenged because this change has happened over only about 30 years. It's insanely fast. So what if we could peer into the future? Other people during the conference have already talked about, what if we had a crystal ball? This was actually an image that my daughter drew for me on a birthday card, because I'm the queen of ice to her. So, isn't that great? But what if we could look into that crystal ball? What if we could create a virtual world and peer into the future? I think the amazing thing is that we can create these virtual worlds. What's perhaps even better is that we have created these virtual worlds. And of course, I'm talking about comprehensive Earth system models, what we also call climate models. These are things that I've spent my career working on. These models are based on fundamental physics. They're based on science that we've been studying for centuries. This is not a new science. These models are skillful, and I'll give you examples of how we test the skillful aspects of these models. They can give us useful information that we can use to plan what we want to do, and which will impact the future. They give us a virtual laboratory that, as a scientist, is an incredibly useful tool for us to do experimentation, to understand how the choices we make today affect the future and affect the Arctic that we will experience in the future. So this conference is all about the Arctic. It's about the future of the Arctic and how we plan for that future. But I think it's important to note that the Arctic is part of a global system. So here's Greenland here. These swirling white lines are weather systems moving around the globe. And you can see that some of those enter the Arctic. They cause precipitation to occur over the sea ice. That's important for how the sea ice functions. You can also see that things happening in the Arctic are affecting lower latitudes. So we have to think of the Arctic in terms of how it interacts with the globe. Also, when you look at this, these cycles and these swirling motions of clouds across our planet, it looks incredibly complex. But if you look at it long enough, you see that there are patterns that nearly repeat. Not exactly, but nearly. There's order in the chaos here. And that's important. That means that we have some hope of predicting that order. As a scientist, that's an incredibly useful thing to understand. And perhaps what's even more useful is that we know that the system is governed by physical laws. There's physics underlying climate science that people have been studying for centuries. This is well established, and we can actually write down the equations that describe these physical laws. So I'm showing you the motion of sea ice. This is taken from a research vessel in the Arctic Ocean. You can see that that sea ice is bobbing in response to winds and ocean currents as it floats on the ocean surface. We can write down the equation that describes how sea ice moves. We can write down the equation on how heat is transferred through the sea ice, how heat is exchanged with the ice and the atmosphere above it, the ocean below, and how all of those things affect the melt and growth of sea ice. We know these equations. We know this physics. And so I'm a sea ice scientist who studies how sea ice responds in the climate system, and so I always start here. But of course, sea ice is part of this interconnected system. There's an atmosphere above it. We know the equations that describe the movement of winds in the atmosphere, how clouds form. Ocean below that sea ice, that ocean can transport heat from the tropics to the poles. Land ice that interacts with the ocean, that land ice moves under the weight of gravity, There's a land system which affects the hydrologic cycle, how heat is exchanged with the atmosphere. And there are ecosystems in the land and the ocean that affect the carbon cycle, how much carbon dioxide can be taken up from the atmosphere, stored in these different aspects of the climate system. So just like we have to understand the Arctic in relation to the whole globe, we also have to understand all these pieces if we're to understand the climate system. And any single piece in all of those components is incredibly complex and rich in its own right. So I'm just going to show that as an example for the land system. So this is actually a schematic from the community land model. And there's urban areas that affect the climate. There's land use change, trees being cut down to grow crops. That affects the climate system. There's snow-covered regions, glaciers, river drainage networks. All of those things interact. All of those things are an important component of how the land acts within the climate state. And I don't expect you to look at all the arrows and words on this. My point is really just that just this piece of the system, the land system, is incredibly complex. It plays a role in heat exchange with the atmosphere, in the hydrological cycle, in biogeochemical cycles, and each individual arrow on this is a scientific study, is someone's career in a scientific field trying to understand how these things work. It's incredibly rich, incredibly complex. This is just the land. This is true for the atmosphere, the ocean, the sea ice, the land ice, et cetera. All these different pieces of the climate system have their own richness and complexity. So the climate system is really complicated. It's global, it's interconnected, it's made up of all these interacting parts. But we do understand the underlying physics, and we have equations that describe how it works. So how do we put this all together and create some sort of useful tool that may allow us to predict into the future? Well, we do this one piece at a time. And so, in terms of the climate models we build, we basically divide the globe up into a three-dimensional grid. That grid goes across the ocean surface and down into the ocean depths, into the heights of the atmosphere, across the sea ice, and we solve our equations on that grid. And what that means is that we can resolve things like ocean currents, the movement of winds in the atmosphere. But it also means that within a grid cell, we have to estimate things. We have to make approximations. So these things are not perfect. There are approximations in them. And not only that, we don't completely understand all of these processes. So we're continually relying on new knowledge gained from observational studies, from theoretical studies, to improve these models. I think there's a real opportunity here to also start gaining understanding from traditional knowledge and using that information on the intricacies of things like sea ice to improve our models as well. And that's something that is really not done currently, but there's an opportunity there. And then we do this for each different piece of the system, the atmosphere, the ocean, the sea ice, the land ice, and we throw all these things together. And then we sort of cross our fingers and hope that this works. And just to note that the way we actually do this is we write it down in computer code. So you don't have to know Fortran. I'm not going to test anyone on this. This is just a piece of code, but these systems are incredibly complicated. They're solving thousands of equations, and our current computer models, climate models, are something like 1 million lines of code. So they're complicated. So what do we end up with at the end of the day? We have these comprehensive Earth system models. They include an ocean, an atmosphere, a sea ice, and a land component. These models started being developed in the 1970s, and they basically included those 4 components. We now also include ecosystems, a carbon cycle, chemistry, land ice. So we are continually improving and expanding these models. The models are designed to simulate the statistics of climate and not the events of a particular year. These are not weather models. And so if you ask me what the temperature in Shishmaref is going to be on January 1st, 2050, that's a question I cannot answer. I can't tell you what the envelope of likely temperatures is going to be, what an extreme warm day will look like, what an extreme cold day will look like. And I can tell you how that envelope of temperatures will shift compared to what we observe today. And the ultimate goal of these systems is to better understand the climate, to understand how the climate works. This is how they've been traditionally used. And I want to note that these systems, because of their complexity, require a team of scientists to develop. They're not developed by a single person. They're developed by a team of scientists with expertise in many different areas. So oceanographers, atmospheric scientists, people that spend their entire careers studying cloud microphysics, sea ice dynamicists, terrestrial scientists. We all work together to build these models. They also require supercomputers to run. So basically, we run these on some of the fastest computers in the world. So they're complicated, they're large systems, and they're developed by teams of people. And what we end up with at the end of the day is a virtual laboratory. So as a scientist, we like to do controlled experiments. I like to just change one thing and look at how the climate system responds. That's incredibly challenging to do from observations alone. So you might look at changes over the latter part of the 20th century and the fact that the climate has warmed. Well, during that time, greenhouse gases have increased. There's been changes in how much sunlight the Earth receives from the sun. There have been changes in volcanic emissions. How can we attribute that change to just one factor? It's very complicated to do from observations alone. These models give us a path forward to do that. So we use these models to do controlled experiments, to ask questions of what if. And traditionally, this has been done by climate scientists trying to understand the climate system. So we ask things like, what if atmospheric greenhouse gases increase? What effect does that have on the system? What if Arctic sea ice declines? We can go into the climate model and we can wipe out Arctic sea ice, and we can look at how that affects the tropics. And when we do that, we see that the tropics warm, that Arctic sea ice loss affects the entire globe. We even do really fundamental things, like we'll wipe out the Rocky Mountains, we'll replace them with plains, and we can say, how does that affect the atmospheric circulation? How does that affect the hydrologic cycle of our planet? That gives us a way to understand the climate system. There's another opportunity here in that we can ask different questions of these models. We can partner with indigenous communities, with decision makers, to ask questions and use these models to interrogate the system in order to make better decisions. So we should all try to work together to make the best use of these tools. And that has not typically been done to date. These models also give us a way to assess issues of climate change attribution. So what do I mean by that? By attribution, I mean determining a causal link between changes we've observed in the system and the drivers of that change, the climate drivers. So the best example, or one of the best examples of this, is looking at the changes in climate over the 20th century. So what I'm showing here is the global average air temperature from 1860 to about 2010. The black line here is the observed change. The yellow and blue shadings here are the envelope of climate model simulations. And you can see that the climate model simulations simulate warming over the latter part of the 20th century, much like observed. These simulations include increasing greenhouse gas concentrations, volcanic emissions, and incoming solar variability. Other than that, these models are just free to evolve based on the equations that are being solved. So we put in these climate drivers, and we get this climate response. And not only do we get the warming in the latter part of the 20th century about right, we get the spatial distribution of that warming about right. So we can ask the question, well, what caused this warming over the latter part of the 20th century? And so we can run simulations in which we change those climate drivers. So these simulations on top, in the blue and orange shading, show model simulations in which we don't allow greenhouse gases to change. We still have volcanic emissions. We still have incoming solar variability at the top of the atmosphere. And you can see that now these model simulations don't simulate warming over the latter part of the 20th century. So we can attribute this warming to rising greenhouse gas concentrations in the atmosphere that are being driven by the burning of fossil fuels. We also use these models to predict future system behavior. And again, these models are free to evolve. They have all these equations that are being solved, but we do have to make some sort of assumption about the climate drivers, and in this case, about greenhouse gas emissions into the future. So these are examples of the greenhouse gas emission scenarios that we use in these models. From 2000 to 2100, a high emission scenario, this is basically the path that we're on currently, middle emission scenarios, and a low emission scenario. Now, we don't know what emission pathway we're going to follow. These are decisions that will be made in terms of our energy infrastructure, the use of renewables, population changes, economic growth. All of those things are going to drive these. So we bracket that uncertainty by using a bunch of different possible scenarios and use those as forcings in our climate model to look at how these different choices that we make in the future will affect the climate of the future. So what emerges when we run these systems? So I'm going to show some visualizations here. On the top, you'll see a present-day climate state, and on the bottom, a future climate state. And this would be at the end of the 21st century. The white is water vapor in the atmosphere. You can think of this as clouds swirling around the globe. The colored areas are sea surface temperatures, and you can see the Arctic sea ice in the polar region. And the time is marching along here over a year. So these models simulate systems, weather systems, that look very much like the observed. And those just arise from the fundamental physics. You can see that these climates are quite different. This is a warmer world. It's a moister world. There's more precipitation occurring in certain regions associated with that. There's implications for things like flooding. You can also see that the sea ice is quite dramatically different in this warmer climate. And you'll see as we move into the summer months, the sea ice melting back over the Arctic Ocean and reaching essentially ice-free conditions sometime in August. So this is a very different world in the future climate. And as I mentioned, when we look at the statistics of the weather and the climate variability simulated in these models, we can see that they look very similar to what we observe. They look like planet Earth. As a scientist, this is actually a remarkable achievement, that we have all this complexity. We throw all these equations together, and these models look very realistic. Sometimes it's difficult to tease apart a satellite image from our climate models. But of course, these models are approximations. They are not perfect. There are biases in the models. There are errors in the models. We know that. And it's even safe to say that these models are not right. But they are skillful. And what I mean by skillful is that the models give better predictions than our simpler alternatives. So say we think that the next 30 years, out to 2050, will look just like the last 30 years. These models give better predictions than those sort of simpler alternatives. And we test the models in all sorts of ways. So we look at how the climate responds to volcanic emissions. And we can see that the models are skillfully representing that. This shows observed air temperatures in the winter following the El Chichon eruption and modeled air temperatures. We can look at the statistics of how these things compare, and we see that the models simulate temperature changes in the atmosphere that look very much like observed responses to volcanoes. We also test these models in very different climate states. So for example, this shows model results from a study in which the model was run for the warm last interglacial over 120,000 years ago, at which time, let's see, orbital changes meant that there was more sunlight entering the Arctic Ocean. And we have proxy information, the kind of things that Kirk talked about earlier today, that tell us that the summer sea ice was thinner, there was a smaller Greenland ice sheet, and when we run our model under these kinds of conditions, that's what it simulates because of changes in the energy received from the sun during this time in the warm last interglacial. And perhaps most importantly, or strong evidence that these models are useful, is that these models have predicted things that have now come to pass. As I mentioned, the first climate models were developed in the 1970s. These models were quite simple compared to what we have today, but even those models predicted that we would see amplified warming in the Arctic in response to rising greenhouse gas emissions at about twice the rate of the global average. These models predicted that before it occurred. We have now seen that come to pass. Models predicted sea ice loss in response to rising greenhouse gases in the atmosphere. This shows the observed record of September sea ice in the Arctic from 1979 to 2018. We've seen things that these models predicted. We could have used that information back in the 1970s and 80s in order to avoid perhaps some of the changes that have actually occurred. So in what ways do our model experiments help inform the future? They provide projections of changing climate conditions subject to certain greenhouse gas emission scenarios. As a climate scientist, they allow us to understand the underlying processes in terms of why things change and how things change. They allow us to quantify uncertainty in our predictions and the sources of those uncertainties. We can look at the uncertainty associated with greenhouse gas emissions and what that means in terms of a future climate. And they provide information on how the choices we make as societies in terms of things like energy generation affect the climate system response. So those are all useful things. So what do these models predict for the future? They predict that we'll see continued warming in the Arctic, continued warming globally, with that warming amplified in the Arctic. And under this particular emission scenario, that warming is dramatic, 8 degrees Celsius, something like 15 degrees Fahrenheit. It's an enormous change. They predict continued loss of Arctic sea ice with the possibility of near ice-free summers later this century. And not only ice-free summers in September, but months of ice-free season length across the Arctic, 3, 4, 5, even 6 months within the Arctic Ocean. That's a dramatic change. They predict continued increases in the melting of the Greenland ice sheet. That has huge implications for that water entering the ocean and causing sea level to rise. So they predict increases in sea level. This shows projections of sea level under a low emission scenario in the blue, a high emission scenario in the orange. This is about 1 meter of sea level rise in the high emission scenario. So that's a big change in which the Arctic is having global impacts, because this sea level rise, of course, will be felt globally. And there are studies done with these sorts of projections to then look at how those things are affecting people. So this particular study looked at the population at risk due to sea level rise in 2100 from this sort of high emission scenario projection. This is just shown for the contiguous United States here, so Alaska isn't included, Europe isn't included, et cetera. So this is just a piece of the puzzle. But all of these orange regions are where populations are at risk of inundation due to sea level rise. Something like over 4 million people at risk of inundation because of sea level rise. And you can imagine the infrastructure cost associated with that. Projected Arctic change has socioeconomic impacts across the globe. And these model projections are used to inform many other studies in terms of how shipping routes might change in the Arctic, at what time, at what location, for how many months. Things like fisheries. We heard some discussion of this in the previous panel. These models can provide information on things like how ocean temperatures, ocean salinity, ocean stability will change, and how that has the potential to impact fisheries. These models are also used to look at infrastructure risk due to thawing permafrost in the Arctic. And you can see dramatic implications for infrastructure across the entire Arctic region, with enormous economic costs associated with it due to thawing permafrost by 2100. So again, the models are not perfect. There are uncertainties in these things. We need to continually improve these models and continually bring in new knowledge that's gained, and also bring in traditional knowledge to improve these systems. But these are the kinds of things that these models enable, these environmental predictions enable. So a lot of what I've shown in terms of the projected impacts for the Arctic are for a high emission scenario, what is often referred to as this RCP 8.5. RCP just means representative concentration pathway. It's not very important It's just different scenarios of greenhouse gas emissions for the future. And this high emission scenario, which currently is about the path we're on, would lead to a very dire future with enormous consequences for the environment and the people that rely on that environment. But we have choices to make here. This is not necessarily the world that we will live in. And you can see that under a medium emission scenario or a low emission scenario, the world looks dramatically different. It's interesting that the pattern of warming actually looks really similar. In all cases, the Arctic will experience more warming than the rest of the globe. But the magnitude of that warming differs by about a factor of 4 here. So whether we have an Arctic warming of 15 degrees Fahrenheit or something more like 4 degrees Fahrenheit is really something that's up to us. We can choose this future. This is sort of a choose your own adventure. We have choices to make, and the path that we choose will make an enormous difference for the Arctic that we experience in 2050. So some final thoughts. I hope that I've convinced you that these comprehensive Earth system models are skillful. They're based on very sound science. They're based on fundamental physics, which we've been studying and understanding for centuries. The models are not perfect. We need to continually improve them. We need to continually bring in new knowledge and new ways to test them. And I think that's an interesting thing, and I hope to have conversations with people in this room about how to do that better over the next couple days. The models are skillful. They have predicted things that we have now experienced. They predicted those things back in the 1970s. So these model experiments can provide insight on how the choices we make today will affect the climate that we live in, or for me, the climate that my children will experience in 2050. And this can help to inform the actions that we take. And the way that we use these models to study these problems is also something that we can collectively decide, because the models are incredibly useful tools, and we can use them in all different ways to get a handle on how our choices affect our future. And that can help to inform the actions that we take. So with that, I'm happy to take questions. And I actually think Twyla, who's quietly sitting over here in the corner, is going to be fielding the questions as they come in on Slido and saying them out loud to me. But I'm happy to take any questions. And thanks so much for your attention.
Marika, there's interest in how long we've been using climate models and how they've progressed over time. And as you look towards the future, are you doing things, for example, to couple models with some of the direct implications, direct impacts that coastal communities might be concerned with, like erosion or wildfires?
Yeah, so to the first question about how they've evolved over time, I mean, we're continually including new pieces of the puzzle. So for example, even 20 years ago, even a decade ago, we typically didn't include land ice models within these systems. We kind of assumed that the land ice was static, it had snow that would melt and grow, but other than that, we didn't worry about how it moved and could affect sea level rise through the calving of icebergs and things like that. Those things have changed. We now have land ice components in these models. So we're continually improving them. We're continually adding new pieces of the puzzle. In terms of things like wildfires or coastal erosion, these models actually do have wildfire components to them, pieces to them. They do simulate how wildfires can change. They have to have a lot of assumptions in that, though. And so that's another piece that's often improving. Coastal erosion, is something the models don't include. It's actually challenging to do because it's happening at a scale that's small relative to how we build these climate models. So there's also a lot of work being done to take the projections provided by these models and use them to inform other models, like a model of coastal erosion, or a model of infrastructure risk, or things like that. So there's different ways that this can be done in terms of linking those things.
Given that models are giving us this different range of outputs, what do you think it needs to be done on the science and then the science linking to policy community to help policymakers use that information, given that we can't provide them a single number?
So we can't provide a single number, but we can provide a range. And I think we can provide what's a range that we are willing to live with. And I think the range is very different in terms of this future climate that we might experience. So I think we already can provide that information. I think we do provide that information. I think some of the challenge with working with decision makers and indigenous and local communities is providing it at a scale that's really useful to, say, an individual community or an individual region. So these models are quite good at providing information on sort of regional scales. They have challenges with providing things at very local scales. And so I think that's actually, I think an area where we need to collaborate more is for scientists like me to better understand what the issues that local communities face, what the issues that decision makers are grappling with, and how I can help to improve our models to better answer those questions. So I use these models as a climate scientist to understand the climate. They're fascinating and very useful and rich tools in that way. But there's a real opportunity for us to better use them for decision making. But in order to do that, people like myself need to better understand what questions decision makers have. So I think that's part of what a conference like this is about, is starting that conversation, having that conversation, starting to actually make those connections to better use these tools.
Folks here talk about tipping points or thresholds, these kinds of ideas. Is that the kind of thing that appears in climate models, or can we use the models to maybe help us come up with some metrics that we need to be following, or a sense of what thresholds may exist and where we would head after meeting that, for example?
Yeah, so these models are used to look for threshold behavior, and they're also used to look at where there are not thresholds. So there's been a lot of work, for example, looking at whether there are thresholds in the Arctic sea ice cover. If you lose it, can you recover the Arctic sea ice, or is it, have you crossed a tipping point such that the Arctic sea ice is completely lost? In that case, we've used these models and experiments with these models to investigate that question, and we do see that if you can reduce greenhouse gas emissions in the atmosphere, you can recover the Arctic sea ice. Things like land ice is a different question and a different challenge. Things like emissions of greenhouse gases from thawing permafrost is another area where the opportunity for thresholds is greater. In some cases, these models are not, so for land ice, I would say the models are still quite simple, and there's a lot of processes that we don't completely understand, and those pieces of the models are improving rapidly, but still don't incorporate all of the processes that are likely important for something like a tipping point. So we can use these models to investigate tipping points. In some cases, the models aren't yet up to the task. So for example, with land ice and how land ice might change in the future. But it's something that that they can be used to investigate those questions.
So you mentioned that you thought there was some real opportunity space for Indigenous knowledge to be incorporated into what's either development or validation or some part of the global climate model production system. Can you maybe envision or imagine an example that you could provide so that people here can start to envision how that might look too?
Yeah. So I think for sea ice, which is the area that I work on most closely, so there's a lot of complexity to sea ice in terms of its heterogeneity, in terms of how snow changes over what sort of spatial scales, and in terms of how those things are changing. Honestly, those are things that we don't represent very well in our models. I expect that Indigenous knowledge, people that are traveling on the sea ice, using the sea ice for hunting, et cetera, have a lot more information on how snow characteristics on sea ice evolve over the seasons, evolve spatially, and are varying over the last several decades where we've seen this incredibly rapid change. That's information that I would love to have a better understanding of and to work collaboratively with people to interrogate and understand how that information can inform our climate models and in terms of what our climate models are simulating for how snow on top of sea ice is changing. So that's just one example. I think there are many other things like that. But there are definitely things where we have to make approximations in the models, and having better understanding of those conditions from people living and breathing those experiences would be really useful.
You talked about and gave us an example for how climate models could help us understand some of the future kind of averages, range, and thinking about climate. Can these models also be useful for helping us understand what drives extreme events?
Yeah, so actually we're doing a lot of work. So the models, like I said, they give an envelope of the kind of changes we might expect in the climate, so the statistics of climate. That includes the extreme events. So they tell us, when what was considered extreme in the last 30 years is likely to become the norm. They can give us information on how extreme events change, both in terms of extreme precipitation events, extreme temperatures. So we can actually, and we do, use the models to look at how changes in extremes occur throughout the system. So extreme events in Arctic sea ice loss, or extreme events in precipitation or air temperature, or ocean conditions. So these models are used to look at all sorts of extremes, and they're quite useful for looking at those extreme events.
Well, I think this is appropriate as we think you've done a pretty good job, I would hope, of convincing the audience here that models have a lot of verification and validation that goes into them. You're modeling past climates and then comparing it with observations to ensure the models are doing a good job. But nonetheless, some policymakers and other folks still aren't very comfortable using scenarios where you're looking at kind of different levels of uncertainty, and the simple fact that models aren't perfect might make people a little nervous about using them. So how do you think we can better communicate that these models still provide useful information for addressing local problems, even if that location's not pinpointed?
I think so. That's a hard question. I think that, to me, the fact that these models predicted things, even at a local level, that have now been experienced in terms of large-scale, decadal scale changes in the climate, is a true testament to their value. I think we're at this critical moment, honestly, in our climate future and the future that we're going to have on our planet. These models gave us information 30 years ago that we dismissed. We should have used that information 30 years ago, honestly. The fact that we didn't, I think, is an enormous shame. And if we didn't use the information that the models are providing now to inform our future, I think we've lost a huge opportunity in terms of having a future that is a future we want our children to live in. So, I mean, I think the proof is the fact that these models did predict things, and we should have used those predictions 30 years ago when they were available to make choices. So, I don't know. I mean, that's important to me as a mother. You know, I have 2 daughters. I want them to have an amazing planet to live on, just like I have. So that's my heart, for those of you who don't think that